Welcome to this explainer. We're jumping right into the invisible, fascinating physics hiding in plain sight during your everyday commute. Seriously, every single time you get in your car, turn the key, and hit the gas, you're kicking off a masterclass in angular kinematics and dynamic forces. And today, we're going to decode all of that. We'll be using your everyday car tires to simplify some pretty complex motion physics, translating all those mathematical concepts into tangible things you can actually feel behind the wheel.
So, let's start with a scenario. Picture yourself in the passenger seat of a car, and the driver suddenly takes a really sharp, fast left turn. What happens? Well, you instantly feel this intense sensation of being thrown outward, right? You get squashed right up against the car door. We have literally all felt this. But what if I told you that your senses are completely lying to you? That exact physical sensation is actually the perfect anchor for our deep dive today, because to understand why you feel pushed away from the turn, we first need to look at how your car moves in the very first place.
Section 1. Rolling tires and angular motion.
All right, let's dive into this by looking at the simplest form of driving, just moving straight forward. Before we can navigate the physics of a tight corner, we have to understand the fundamental relationship between a spinning wheel and the road beneath it. When you drive, your engine isn't just magically pushing the car forward, it's spinning the tires. If you mentally zoom in on the very bottom of the tire, that little contact patch where the rubber actually meets the asphalt, something cool is happening. As the tire rotates, a point on its outer edge moves at a specific speed. Assuming you aren't slipping or doing a burnout, the speed at which that outer edge spins perfectly matches the forward speed of your car over the ground. The rotational spin of the tire directly translates to your linear forward movement.
There's a beautifully simple equation for this relationship. Tangential velocity, or v, equals omega times r. Now don't let the math scare you. In this formula, v is just the linear forward speed of your car. It's literally the exact number you're reading on your speedometer. Omega represents the angular velocity, which just means how fast the tire is spinning in a circle, and r is the radius of your tire. This formula tells us exactly how the spin and the physical size of your wheel dictate your real-world speed. In fact, if you were to put larger tires on your car, increasing that radius, the exact same amount of engine spin would actually result in a faster forward speed.
Section 2, the physics of the turn. Okay, now that we've got the car moving in a straight line, let's turn the steering wheel. As we approach a flat curve, the physics get a whole lot more complex. We're moving from simple rolling motion into the realm of uniform circular motion. Whenever you turn the wheel, the car's velocity changes direction. And in physics, any change in direction requires an acceleration, which in turn requires a net physical force. On a standard flat curve, the single crucial force keeping your car from flying right off the road is just friction. Specifically, it's the static friction between your rubber tires and the asphalt, pointing directly inward toward the center of the curve. We call this inward pointing force the centripetal force.
We can calculate exactly how much of that inward grip you need using the centripetal force formula. It says that this force equals the mass of the car times the velocity squared, all divided by the radius of the turn. So why does this matter to you as a driver? Well, the force you need to safely make a turn increases directly with your car's mass. Heavier cars just need more grip. But look at the velocity part, it's squared. That's a massive deal. It means taking a corner at 100 kilometers per hour doesn't just require twice as much friction as taking it at 50, it requires 4 times as much force. On the flip side, if you take a wider turn, meaning you increase that radius, the required force actually goes down.
Section 3. The centrifugal force myth. And that brings us right back to the elephant in the room. Let's revisit that question from the beginning. If the only real force in a turn is friction pulling the car inward, why on earth do you feel pushed outward against the door? Well, we have to talk about centripetal force versus the forbidden F word of physics, centrifugal force. Centripetal force is absolutely real. It points inward and relies on actual physical interactions, like the friction from your tires. Centrifugal force, on the other hand, is completely fake. It's a fictitious force. It doesn't actually exist in our stationary frame of reference. There is absolutely no invisible hand pushing you toward the outside of the car. What you're actually feeling there is just your own body's inertia. According to Newton's first law, your mass just wants to keep traveling in a straight line at a constant speed. The car is what's turning inward, off that straight path. You aren't being pushed outward into the door is physically turning inward and running into you.
There's a classic demonstration that captures this illusion perfectly. Imagine rolling a tennis ball completely straight across a flat whiteboard. But as the ball rolls, you start spinning the whiteboard underneath it.
If you were somehow sitting on that spinning board, it would look like the ball was magically curving outward toward the edge, being pushed by some invisible centrifugal force. But if you were an observer looking down from above, you'd see the absolute truth. The ball is moving in a perfectly straight line. The outward sensation is merely an illusion created by relative motion. In the car scenario, you are the tennis ball, and the turning car is the spinning whiteboard.
Section 4. Banked curves and engineering. So what happens when we push cars way beyond the limits of regular road friction? We move from flat roads to high-speed racetracks, and this is where engineers have to essentially manipulate physics through road design. They solve the problem of high-speed turns by banking or tilting the road inward. Let's walk through how this works, step by step. First, the road is tilted inward. Second, gravity is still doing its thing, pulling the mass of the car straight downward. Third, the road pushes back up against the car. This is called the normal force, and it always acts perpendicularly away from the road's surface. But here's the kicker. Because the road is tilted, this normal force is also tilted, and that means a horizontal component of that normal force is now pointing directly inward toward the center of the curve. The actual structure of the road is pushing the car through the turn. When you contrast an unbanked flat curve with a banked curve side by side, the engineering trick becomes super obvious. On a flat road, you're relying 100% on the friction of your tires to generate that inward centripetal force. If you go too fast, or if the road is slippery, the tires fail and you slide out. But on a banked curve, that inward pointing component of the normal force takes over. The geometry of the road itself is providing the necessary inward acceleration. This dramatically reduces the strain on your tires, which is exactly how race cars on heavily banked tracks can take corners at mind-bending speeds without relying entirely on the rubber grip.
Engineers even have a specific formula to calculate the absolute perfect tilt for a road, known as the banking angle formula. It states that the tangent of the banking angle equals the velocity squared divided by the radius times gravity. Now look closely at that equation for a second. Notice what's missing? Mass. It's completely gone. The ideal banking angle is completely independent of the car's mass. Whether you're driving a massive semi-truck or a tiny little sports car, if you enter that curve at the designed optimum speed, the horizontal normal force perfectly balances the required centripetal force. In a perfect scenario, you wouldn't need any friction at all to make the turn.
But, of course, most of us aren't driving on perfectly banked racetracks, so how does this translate to your actual safety on normal unbanked roads? Let's look at some real numbers from our sources. Imagine driving a 1,200-kilogram car around a 50-meter radius bend at 15 meters per second. The physics demand 5,400 newtons of inward centripetal force. That means you need a friction coefficient of 0.51 from your tires. On safe, dry tarmac, your tires usually provide a coefficient of about 0.7, so you've got plenty of grip. The turn is completely safe. But what happens on wet tarmac? That available friction drops to around 0.40. The physics still demand 0.51, but the road can only give you 0.40. The friction is insufficient, and at that speed, on that wet road, you are definitely going to skid outward.
Which leaves us with one final, kind of terrifying, but deeply illuminating scenario to think about. Imagine you're taking a sharp left curve, relying entirely on the friction of your tires, and suddenly, right in the middle of the turn, you hit a patch of pure, frictionless ice. The friction drops to absolutely zero. The centripetal force vanishes in an instant. Ask yourself, what path will your car actually take? Think back to Newton's first law. Without that inward force, your car doesn't magically get thrown outward from the center. Instead, it instantly stops turning and continues in a perfectly straight line, completely tangent to the curve, flying straight off the road. The physics of the drive are always at play, constantly binding your tires to their tangents. So next time you take a sharp turn and feel pushed against the door, just remember, it's not you flying outward, it's just the car pushing you inward. Thanks for joining me on this explainer. See you next time.